Hey guys, this is part 3 of the USB hub series. This video is going to go into a good portion of the schematic design, everything up to the power, the input power, the output power, and ESD protection, EMC, kind of stuff like that. But before I jump into the video, once again, if you have not already, please do join the Discord. It's absolutely taking off. It's a really cool time. The link is in the description. So I often get asked, and on the last live stream I did, I kind of went into it a little bit on how I do hierarchical sheets. And I think hierarchical sheets are one of the most useful features of a ECAD software, and also one of the most misused, because you can make a schematic that would otherwise be relatively easy to read an absolute nightmare by using hierarchical sheets wrong. But the opposite can also be true. A lot of designs lend themselves very well to using hierarchical sheets, and if you don't, it just becomes cluttered. So basically, and this is kind of new to me in the last maybe 3 or 4 designs that I've done, I never used to use hierarchical sheets, or I would only use them for blocks that repeated over and over again, because that is kind of the obvious use case. But I've started using them on pretty much any intricate design, because it really abstracts out a lot of the like nitty gritty of the inner workings. So my whole goal when I'm doing a hierarchical design or using hierarchical sheets is to abstract out any of the anything that's not useful for the overall picture of the design. So decoupling capacitors, your power input filtering, your GPIO lines that are high or low for configuration, your unused pins, that's a big one. So for example, with the MUX, any of the decoupling caps, any of the pull-ups, any of the filtering, the series resistors, those will be inside the hierarchical sheet. But every pin, and this is something I try to be very cognizant of, is when you are outputting a hierarchical label, I make sure to always do it with the exact name of the pin it represents. And it's not overly important for this design, but since when I'm doing projects for work, I'm not the one doing the programming, it makes it really easy from our programmer's perspective to be able to look at this high level and say if this was a microcontroller. They don't have to get down in the weeds and look at all of the circuitry stuff. All they have to look at is, oh, okay, pin whatever this is going here. Pin whatever this is going here. And the only way that works is if you keep the name exactly the same. So I try to do my best with that, but it really is pretty important, and it makes it a lot easier to read. And the other thing I did on this project, which is very cool, but and it's only new in KiCad, which will be 5.99, is alternative pin assignments. And it's not done really well in here. It's really clunky to change, but it is really clean. So for the out pins 1, 2, and 3, these are typically the I2C lines. So you would have your SCL, SDA, and your interrupt. Normally in KiCad or in, I actually don't know what other ECADs do this because I've never used them before. I've never used alternative assignments. But normally you would put SDA / out 1. And then for whatever you're using, you would just use both of them on the same pin. But it's kind of clunky because right now I have this configured to not use I2C. So I shouldn't have I2C. So it lets you, by going in here, toggle which one you want to use, either the interrupt or out 3. So I used that pretty heavily in this design, not as much for the MUX just because there wasn't a lot, but for the USB hub, there were quite a few. And this hub has kind of been a nightmare. I am sure that I'm going to be missing at least 1 or 2 configuration pins. There's a lot here. since this design does not use I squared C or SPI, everything on here is done with strap pins, and you have to make sure that all of your strap pins, whether they are pulled up or pulled down or floating, are correct based on the data sheet. And that's really, for the schematic side of this project, that's going to be the hardest part. And it's easy to get kind of scared away when you see a project that seems this involved. But really, the vast majority of the time that I spent on this was looking at the data sheet and going pin by pin to make sure that they were set correctly. So with that out of the way, I think what I'm going to start with first is just do a kind of an overview and just kind of the general functionality of this, what I still have to do. And then afterwards, I will go into some of the pin assignments. I don't want to spend the entire video just for all of the configuration, but I'll at least mention them a little bit. So on the input side, we have our single USB port, our USB-C, and that's considered an upstream facing port. So this is what is facing your desktop or laptop computer. So like I said in the intro, I do not have any ESD protection on this. That I will cover in which I'm assuming will be the last schematic video, so part 4. And what I do there is simply I will move this over, and then I'll add a USB-C filter hierarchical sheet and pass everything through here, and internally it will do the filtering in that sheet. Because again, if you're looking at this to see what's going on, it'll say USB-C ESD filter. That gives you all you need to know about it, and if you want to know exactly what's going on, you enter the sheet. So for the Type-C port, we have the input VBus. Since this USB port, as voted on by you guys, it will be powered externally. So all this VBus is going to be used for is detection on the MUX and on the hub side. We're not actually going to be taking and using that 5 volts for anything, maybe a LED or something like that. So I have a label on here, but that's about it. Our CC pins, which are used again to make sure the orientation we know, they're crisscrossed on it. So depending on how it's rotated, they will either be, one will be pulled up or the other one. And the MUX is what uses that information to flip the inputs. The D+, D-, you technically can use a MUX here to flip it, but these are opposite corners, so you can just tie D+ and D- together. That's what I would assume most people do. I did read there is a reason to use a MUX for certain situations, but for the most part, it's not needed. So basically, USB 3 and above that uses the separate differential pairs, they have what are called AC coupling capacitors. All these do is they block DC voltages, so it doesn't matter. It does a few things. One is it makes sure that on the data lines, they're electrically isolated from DC voltages, so it prevents you from getting any ground loops between these. It also prevents if you happen to have a common mode voltage here that is a lot different from your common mode voltage here, the differential pairs will tend to be more sensitive to that because you can't have as much protection from Zeners or TVSs like you can on the slower speeds. So that protects them because it doesn't matter what the voltage is here on the DC side, it's not going to get passed through. And one weird thing about Type-C, I mean, it's not weird, but one thing that takes some time getting used to is only the transmitting side has the AC caps. So the RC side will actually just pass through. So like I mentioned in the first video, this has 2 sets of differential pairs. Only one are used at any time. So either TX1 and RX1 will be used, or TX2 and RX2. depending on how the cable is inserted, because it can be inserted both ways again, that determines which one of these pairs will be used. The MUX takes the CC pins, and depending on checking VBus to make sure there's actually a device there, it will combine whichever two differential pairs are used, and then it literally just ports it to our single differential pair output. So from the MUX, it goes straight into our USB hub by using, again, routing the single differential pair out. And like I said before, we only have the AC caps on the transmitting side. The receiving side does not require them. For the USB 2, it doesn't use AC coupled caps, so we never have them. VBus route straight in, and then from here, depending on how many ports of the USB hub are used, this is only using 4. Remember, this port has 6, but the 6th is only in USB 2.0, but I did not want to do any more ports than I had to, so only using 4. Each one of these outputs have the USB 3.0 differential pairs. Again, AC coupling on the TX side. It also has a single USB 2 differential pair, and then it has this port control. This port control is basically used in conjunction with our power controller to go downstream, and it's used to signal if there's an overcurrent condition, if it needs to be shut off. So that I will cover in the next video when the power section is finished. So all of that repeats, and then all of these go straight down into the 4 type A outputs. And another thing that I think is really, really important with hierarchical sheets is you should never have a connector that is buried within a hierarchical sheet, because that goes against exactly what I'm saying when I do these. Is my goal for it to be easy to understand it only by looking at the top level. And if you bury a connector in a sheet, you have no idea. So connectors always have to be on the top level. Anything intricate on the inside can go internal to a sheet. So the output, no ESD protection. That will be, like I said, in the next video with a filter block right in between here, just like it is on the upstream side. And what's cool about doing it that way is all of these are going to have identical protection. So it will be a single schematic that's just duplicated 4 times or referenced 4 times. So saves space, saves time. We only have to do it once. So now digging into the internal sheet of the MUX first. So the biggest thing with both the MUX and the hub is both of them can operate on GPIO mode, or they can operate on I2C mode. So the first thing was determining how to do that. And the MUX was pretty easy just because there wasn't a lot of pins and there weren't a lot of options. So based just on the data sheet, by checking for the address pin, that is how you determine what mode it is set into. So for GPIO mode, we set it into floating. So we throw on a non-connect and we call it a day. For the vcon fault, that is a open drain output for if there's an overcurrent event. We don't have a microcontroller on here, and I don't want to have a LED for something like that. We float that. For ID is basically the exact same thing, but it shows when there is a device attached. Maybe that would be useful for an LED, but I floated that as well. For the out pins, those were a little bit more useful. So like I said, with the alternative pins, these are either SDA, SCL, or an interrupt. For out 1, and this I actually posted in the Discord when I read this, they have a typo, or they don't really know what they're talking about. So if I2C is enabled, it's I2C communications, pull up, good to go. If it's in GPIO mode, so the address is no connect, it's an open drain output for communicating the current mode detection when it's in an upwards facing port mode, which this is. But then they give you the logic diagram as high and low, which an open drain can only float or go low. So either this was supposed to be float, or I guess only GPIO mode is an open drain. Either or, it's wrong the way that they wrote it. So my assumption is this is just supposed to be floating, and they're making the assumption that you are going to have pull-ups. So with a pull-up, now the two outputs will read like that. And out 2 does the exact same thing, except it just gives you one more configuration point for what the upwards facing port can source. These actually aren't going to be needed most likely, since we are not going to be using the upstream facing port for power. I have them on here just kind of to show how that would be done if we were sourcing power. So depending on what the current draw allowed from our upwards facing port or upstream facing port, these out pins would then go to our USB hub, and that would determine how much each port can source. But since we're going to be using an external power supply, we don't really care what the upstream port can source, but it's there if we need it. Then the DIR pin is basically just used internally for the orientation. So we tie it to the 3v3 volt and call it a day. So the last couple pins are the port and then the current mode. Port simply determines if we're an upstream facing port or what our configuration is. Low is UFP, so tie it to low. Current mode is if we're advertising as a downstream facing port, which we're not, so we can just float that. It says don't care in UFP mode, so keep it floating, that works. And then VBus detect is just what it uses to detect the VBus. They want to just have an external resistor. And then for ease of use on the hierarchical sheet, I have the USB 2 passing through, the VBus detect passing through as well. So that just makes it convenient to pass through the USB 2 straight to the USB 2, the VBus detect straight to the VBus. So nothing's done with those and nothing's going to be done with them. So next is the USB hub, and this one was a heck of a lot more interesting. So first there's a group of test pins. These are used just internally. It tells you exactly how to set them up. So I just listened there. Our bias is just a pull down with a specific value. It's used for internal biasing one of the current sensors, and just tie it straight like they say. PF29 is just a non-connect. SPI is disabled. The next one is for the configuration strap BC enable. This determines if battery charging is enabled on the downstream ports. The CFG non-removable is just what ports are removable. That's what that one is. The CFG straps, these are really weird. It tells you exactly what to set them to. The I2C lines we're not using, so we use the weak pull down to pull them down. For the port control pins, this was one of the more confusing things to kind of figure out. So the port control 1234/OCS is over current sense, and this also talks to the downstream power supply or the current sense, and this is used to determine if there's an overcurrent issue and how to handle it. The other pins that are the _U3, that's if we're using what is called port split. Since I haven't done USB 3, this took me a while to figure out. Basically what that is saying is if this was going to say an internal microcontroller, you can route just the USB 3 to that, and then also use the USB 2 separately in a hub configuration. So it splits the ports, like the name says. Really useful. I didn't know that that was a thing, but it took a while to figure that out. Since we are not doing that and all sets of these are going to a single port, we can just keep them floating and disable that. I squared S, we are using again a weak pull down for since we're not using any of the audio configuration. The VBus monitor monitors the upstream port. These are your upstream 3.0 and 2.0 lines. The downstream are just the pairs going down. For the unused ports, it was again really goofy in what the configuration was, but based on the data sheet, you either had to pull them up to 3v3, down with a weak pull down. Here I used 10K. I guess that should be 47, and then the other pulled back to 3v3. So the last thing with the USB hub side is the power portion, and this, like I did in the second video, this has 2 units. So this is just for the power side. And for the decoupling, there are 2 different power rails, the 3v3 and then the V core. The V core is either 1.5 or 1.2 volts nominal, I forget, but that will be tied in from the outside of the hierarchical sheet. Both of them need to be thoroughly decoupled. This, and I mentioned before, this is one of the only bigger high-speed ICs that I've ever seen that only has a single ground pad, and it's the thermal pad, which it'll make the layout kind of, I guess, interesting or just kind of neat to mess with because I've never done that before. But every one of the VCC pins or the VDD33 pins and the V core needed decoupling. And when we're working on the layout, probably we'll add a local bulk bypass cap for each one of these as well, but we'll see how the layout ends up. And then for the crystal, just a 25 megahertz crystal with a set of 33 picofarad load caps. And I did just the standard load capacitance calculation to see how much it should be. So that pretty well sums up what the schematic looks like so far. I will have the link to the GitHub repository. I have everything on here, and I'm uploading it, or I'm making commits as I go. So even before the next video comes out, I will have changes that are more up to date than the video. So if you want to see all that, go ahead and check out the repository and star it so you can get updates. But otherwise, as always, please let me know if you have any comments or suggestions, and I hope you enjoyed, and I will see you in the next video.